Fast River, play.
On the Supercharged World of Chemistry Program 8, we're going to start off with the ideal gas equation and float on from there. A few sample problems will help us understand Dalton's law of partial pressures. Next is intermolecular forces, the forces of attraction between molecules. You'll find out why gases can condense into liquids and vice versa. It's better than magic.
It's time for a pop quiz. If you double the amount of gas in a container, what happens to the pressure of the gas? A, it doubles. B, it quadruples. C, it stays the same.
Look! Up in the sky!
What, the bird?
No!
The Standard Deviants present the Supercharged World of Chemistry.
Starring Galila Azraz, Gabrielle Smith, Jeremy Clavens, Dina Rubenson, Malcolm Smith, Trevor Dean, Chuck Hinshaw, Christiana Celeste, Tessa Monroe, and Chaz Maston.
Section A, Kinetic Molecular Theory.
So gases act differently than solids or liquids. Kinetic molecular theory explains why gases act the way they do.
All these theories. Can't chemists ever just say anything for sure?
You could say one thing for certain. You are getting on our nerves.
The kinetic molecular theory is based on these 5 assumptions.
Number 1. A gas is composed of molecules that are far apart from each other in comparison with their own dimensions. So most of the volume a gas occupies is really empty space.
I'm just a gas in space!
2. Gas molecules are in constant random motion. Each molecule continues to move in a straight line unless it collides with another molecule or with a wall of the container.
3. The molecules exert no force on each other or the container until they collide with each other or with the walls of the container. So if a gas molecule is just cruising around in space, minding its own business and not running into anything, it's not exerting any force on its fellow molecules or the container.
Hey, I'm just cruising. I'm not bothering anybody.
Oh yeah, till you ran into me, you idiot!
The average kinetic energy of the molecules of a gas is proportional to the temperature. This one sounds complex, but think about it this way. When you heat up a pot of water, the molecules start moving really fast. Then they escape from the pot, or boil off. The movement of the molecules is the kinetic energy. As the temperature goes up, the molecules move faster. The more heat there is, the faster the molecules move. So, the kinetic energy is proportional to the temperature.
And number 5, every time a molecule collides with the wall, it exerts a force on it.
Uh-oh, we do that.
And here's an effect of this rule number 5. If you decrease the volume of a container of gases, in other words, if you make the container smaller, the number of molecules per unit of volume increases. So, if you put the same amount of gas in half the volume, the pressure of the gas doubles as a result of increasing collisions with the wall. This phenomenon is called Boyle's law.
Half the size, twice the pressure. Boyle's law.
Now let's go over diffusion and effusion, 2 important properties of gases.
Gases can also diffuse and effuse. Diffusion is the process by which one gas mixes with another.
Effusion is the process by which a gas escapes from a container through a very small hole, like if you open a helium-filled balloon and let the helium escape. The helium gas diffuses into the air, and once the molecules escape through effusion, we can say they feel, well, effusive.
The rate of diffusion, or effusion of a gas, is inversely proportional to the square root of its molar mass. What the heck does this mean? Well, simply this. The heavier a gas is, the slower it diffuses or effuses. This phenomena is called Graham's law.
Not only am I a snack food, but I made a law. Once again, my law states the heavier a gas is, the slower it effuses or diffuses.
Section B, the ideal gas equation.
Chemists, wacky idealist dreamers that they are, came up with an equation to describe how gases ought to behave. It is called ideal gas equation, and it is useful because it shows us the pressure, volume, and temperature, as well as the moles of any hypothetical gas. We use this equation constantly to describe and understand the behavior of gases. Of course, the equation is hypothetical, since in real life, there are always factors that throw a monkey wrench into the works and skew the numbers. But hey, that's why it's called ideal. You can remember the equation, PV equals nRT, because it looks kind of like PervNERT.
In the ideal gas equation, P represents the pressure of the gas, V equals the volume, N equals the number of moles we're working with, and R is the gas constant, and T is the temperature. R, the gas constant, is one of those deals you can just look up in your book. It's 8.314 joules per mole times Kelvin, or 0.0821 atmospheres times liters per moles times Kelvin. Either one works in the equation. You can choose which form of the gas constant you use, depending on whether you need to work with joules, a unit that measures energy, or atmospheres, a unit that measures pressure. So the gas constant doesn't change, and that's why it's called a constant. You can use the ideal gas equation to find the partial pressure of a gas.
The partial pressure of a gas in a mixture is the pressure exerted by one of the gases in the mixture. Dalton's law of partial pressure says that in a mixture of gases, the total pressure exerted is the sum of the pressures that each gas would exert if it were present alone under the same conditions. So the total pressure equals the pressure of the first gas, plus the pressure of the second gas, plus the pressure of the third, and so on. So you would use the PervNERT ideal gas law to find the pressure of each gas, and then use Dalton's partial pressure law to find the total.
Here's an example. Suppose we have a 1-liter flask containing 5 grams of carbon dioxide and 2 grams of oxygen molecules, and the temperature is 25 degrees Celsius. We have to find the partial pressures of each of the gases and the total pressure in the flask. We can use the ideal gas equation, PervNERT, but first we have to rearrange it so it's more useful to us. We'll set up the equation so it finds the pressure P, which is what we're looking for. Use some algebra to rearrange the problem.
Algebra?
It's not that bad. Just divide the whole deal by the volume. So the equation now looks like this. Pressure equals the quantity of the number of moles times the gas constant times the temperature divided by the volume.
Pressure? Don't tell me about pressure. I feel pressure from above, pressure from below.
Let's start by converting our temperature from degrees Celsius to kelvins. That's really easy. Just add 273.15 to the degrees Celsius, and we get 298.15 kelvins.
Remember, to go from Celsius to kelvins, just add 273.15.
Now we have to determine how many moles of each gas are in the flask.
This is the equation we'll use for the conversion. N, the number of moles, equals 1 mole of your substance over the weight of 1 mole of your substance in grams times the mass of your sample.
And here's a quick reminder about finding the weight of your substance in grams per mole. If your substance consists of a single type of atom, you can look up the mass of that atom in AMUs in the periodic table. Then, since 1 mole of any type of atom has a mass in grams equal to the atom's atomic mass measured in AMUs, you can literally just change your units from AMUs to grams per mole. The mass in grams of a compound that's made up of crystals, like NaCl, is called the formula weight. The formula weight is just the sum of the masses of the atoms in the compound's empirical formula. The mass in grams per mole of a substance that consists of molecules is called molecular weight. To find molecular weight, take the mass of each of the molecule's component atoms in AMUs and add them up. So for instance, to find the mass in grams per mole of the oxygen molecule in our pressure example, just find the mass of oxygen, multiply it by 2, and slap the unit grams per mole on the end. So here we go, converting our sample of oxygen from grams to moles so we can find its partial pressure in the flask. N, the number of moles of oxygen molecules, equals 1 mole of O2 over the weight of 1 mole of O2 in grams, 32 grams, times our sample, 2 grams of O2. Multiplying our sample, 2 grams, by 1 mole of O2 over the mass in grams of a mole of O2 is like multiplying by 1, so it changes units without changing amounts. See, if you weighed out 1 mole of oxygen molecules, it would weigh 32 grams. So in effect, 1 mole of O2 and 32 grams of O2 are the same thing. That's why it's like multiplying by 1. 1 mole of O2 over 32 grams of O2 multiplied by our 2 gram sample gives us 0.0625 moles of oxygen molecules.
Remember, the ideal gas law, PERV-NERT, is rearranged to solve for pressure. Pressure equals the quantity of the number of moles times the gas constant times the temperature divided by the volume.
Now let's plug the numbers into our equation to find the pressure of the oxygen in the flask. The pressure equals the quantity 0.0625 moles times the gas constant. Now you need to choose one of the 2 gas constants. Since we want pressure, and since the total flask is measured in liters, use the one in atmospheres and liters. That's 0.0821 liters times atmospheres per moles times Kelvin. Those 2 quantities are multiplied by the temperature, which we determined was 298.15 kelvins. And all that is divided by the volume, 1 liter. Now here comes a little more algebra.
Relax, it's not hard.
The denominator in the gas constant, moles times Kelvin, shifts down to the denominator of our equation. So we'll cross out all of the terms in the equation and multiply the terms in the numerator. That leaves us with 1.53 atmospheres, the pressure of the oxygen in the flask.
On to carbon dioxide. We have to convert from grams to moles again. The number of moles of carbon dioxide equals 1 mole of carbon dioxide over the molecular weight of 1 mole of carbon dioxide, 44 grams, times the weight of our sample, 5 grams. That equals 0.114 moles.
Now we're ready to find the pressure of the carbon dioxide in the flask. The pressure, P, equals the quantity of 0.114 moles times the gas constant, 0.0821 liters, times atmospheres per moles times Kelvin, times the temperature, 298.15, all divided by 1 liter. Again, we'll move the denominator of the gas constant to the denominator of the equation and cancel out the units. That gives us 2.79 atmospheres, the pressure of the carbon dioxide in the flask.
Finally, to find out the total pressure in the flask, just add up the individual partial pressures. 1.53 atmospheres plus 2.79 atmospheres equals 4.32 atmospheres. So the total pressure is 4.32 atmospheres.
But now, a bit more about moles. There is a simplified version of the equation to convert grams to moles that your esteemed chemistry professor will probably expect you to know. It's really quite simple.
Here's the equation you've been using to convert from grams to moles. Like we said, it uses the unit factor method to change units from grams to moles by multiplying the weight of your sample by 1 mole of the sample over the molecular or formula weight of the sample in grams per mole.
Grams to moles. Grams to moles.
Now here's the simplified version. You can just ignore the 1 mole of substance in the numerator because it doesn't do anything for the values in your equation. Just take a shortcut and put the mass of your sample right over the molecular or formula weight in grams per mole of your substance and calculate it that way.
So for instance, this is how we converted carbon dioxide from grams to moles in the pressure calculation we just did. Let's do it again using the simplified version of the equation.
We'll put the mass of the sample of carbon dioxide, 5.00 grams, over the molecular weight of carbon dioxide, 44.0 grams per mole. So cancel out the grams and divide 5.00 grams by 44.0 grams per mole, and you get the same answer you got before, 0.114 moles.
Enough about the moles already. Get back to the gases.
When you work with the ideal gas laws, keep in mind that there will be deviations from ideal behavior.
In real life, gases don't obey the law. 2 excuses the gases have for not obeying the ideal gas law are 1. When the molecules are crammed into a very small space and the pressure is high, the molecules take up a significant fraction of the empty space, and this can skew your results. And 2, there are intermolecular forces acting between the molecules. Now, what the heck are intermolecular forces? Stay tuned!
So, the ideal gas equation describes the pressure, volume, and temperature of any hypothetical gas. You can rearrange the ideal gas equation to find the partial pressures of gases in a container. Then, if you add up the partial pressures, you get the total pressure of the gases in the container. It's important to remember that the ideal gas equation describes hypothetical gases that behave exactly like they're supposed to. In real life, gases just don't always behave like the ideal gas equation says they should.
Part 3. States of matter. Section A. Intermolecular forces.
Intermolecular forces are the forces of attraction between molecules. They are not as strong as ionic and covalent bonds, but they definitely have an effect on states of matter. The intermolecular forces operating on gas molecules are not that strong, and they allow gas molecules to move away from each other. The intermolecular forces between molecules in a liquid are a bit stronger, so liquids hold together and assume the shape of whatever container you put them in. Solids have strong intermolecular forces at work between the molecules, locking the molecules in place.
Intermolecular forces are responsible for the condensation of gas molecules into their liquid state. Gas molecules normally move pretty fast, but as the temperature decreases, the speed, or kinetic energies, of the molecules also decrease. As gas molecules slow down, they begin sticking together, and when they finally do stick together, they form a liquid. This change of state from gas to liquid is a result of intermolecular forces, the forces that made the molecules stick together.
Intermolecular forces! Intermolecular forces!
In the liquid state, the molecules still have some kinetic energy, although the liquid is more dense than a gas. As the temperature continues to fall, the molecules lose more of their kinetic energy. With less kinetic energy, the molecules slow down, and the attractive forces between them cause them to congregate and solidify. Here comes another change of state. Presto, we have a solid.
There are 4 types of intermolecular forces, all with funny names. They are ion-dipole interactions, dipole-dipole interactions, London dispersion forces, and hydrogen bonds.
Ion-dipole interactions exist when a solid substance made of ions is dissolved in a liquid consisting of polar molecules. For example, when sodium chloride, an ionic solid, is dissolved in water, a polar liquid, the solid salt crystals break up and form the ions, Na positive and Cl negative. The positive charge on the polar molecule moves towards the negative ion of the salt and vice versa.
The term dipole is just another word for polar molecule. Dipole-dipole forces result from the slight charges on the ends of polar molecules, causing them to stick together. It's the dipole-dipole forces between water molecules that cause bodies of water to have surface tension. These forces are relatively weak because the charges on polar molecules are pretty small. But even the small polar charges are enough to create a tangible force. And when you do a belly flop into the pool, ouch! You definitely notice the dipole-dipole forces between the water molecules. The polar molecules try to hold together.
London dispersion forces are intermolecular forces that result from fluctuating instantaneous dipoles. I'll explain in English. You can't have dipole-dipole forces between nonpolar atoms and molecules, right? Because there are no charges attracting the molecules to each other. But a guy named Fritz London... Who? Fritz London. He figured that since nonpolar molecules can become liquid, there must be some intermolecular force at work between nonpolar molecules. So he came up with this idea of instantaneous dipole movement.
Fritz London figured that even nonpolar atoms like helium might sometimes have both their electrons on one side of the nucleus for just an instant. Old Fritz called this coincidence instantaneous dipole movement. For just an instant, a normally nonpolar atom or molecule is polar. Then, of course, the electrons move and the atom or molecule isn't polar anymore. But when one atom becomes polar for an instant, the force of its electrons on one side repels the electrons on the atom that's next to it, making that one polar for a moment by shoving both of the atom's electrons to one side. This can continue in a kind of domino effect until a whole bunch of atoms are polar for an instant. When this happens, you get a real quick and temporary dipole-dipole type attraction between normally nonpolar particles. London dispersion forces operate between polar molecules too, increasing the attraction between the polar molecules.
We're here in London. The dispersion forces have begun the bombing, pushing our electrons to one side, which makes us polar for just an instant.
hydrogen bonds are intermolecular forces too. And guess what? They deal only with hydrogen. When a hydrogen atom bonds to a strong electronegative atom, it forms a polar bond. The electronegative atom pulls hydrogen's electrons toward itself. The hydrogen, with its electron pulled away from it, has a tiny positive charge. It is then attracted to an unshared electron on another atom. This attraction, found in molecules like water and hydrogen fluoride, is the last type of intermolecular force.
So, intermolecular forces are the forces of attraction between molecules. Ion dipole forces, dipole-dipole forces, London dispersion forces, and hydrogen bonds all make molecules stick together. Intermolecular forces can cause gas molecules to stick together to become a liquid, and, in the case of solids, they can lock molecules rigidly in place.
Section B, phase diagrams.
A phase change is a transformation of a substance from one state to another. When ice melts, the substance water is changing from its solid phase to its liquid phase. Now, as water boils, it goes from its liquid phase to vapor, its gaseous phase.
A phase diagram shows us what phase a substance is in at particular temperatures and pressures. At low temperature and high pressure, a substance is generally in its solid phase. At high temperature and high pressure, the substance is generally a liquid. And at high temperature and low pressure, the substance is usually a gas. When two opposing processes are occurring at the same time, for example, if a liquid is evaporating and condensing simultaneously at the same rate, it is called equilibrium. The lines on the diagram represent the equilibrium point between states. The intersection of the three lines on the diagram is called the triple point. This point represents the pressure and temperature at which all three phases are at equilibrium. In other words, at the specific pressure and temperature indicated by the triple point, a substance moves between its liquid, gas, and solid phases simultaneously and at the same rate. So, a phase diagram gives us a nice graphical summary of the phases of a substance.
Carbon dioxide, CO2, is a colorless gas with a faint, sharp odor. This versatile molecule is a jack of all trades. Plants use it in photosynthesis to make carbohydrates. It's also the bubbly in your soda.
It's pop quiz answer time. The question was, if you double the amount of gas in a container, what happens to the pressure of the gas? The answer is A, it doubles. This phenomenon is called Boyle's Law.
This is PBS.
Loading. Disc player. Home for Mitchell Edward Coleman. Button. Press cross to select. Horizontal list 3 of 7. L1 button or R1 button switch homes. Options button. Options. For more content, press the down button.